Welcome to a video on precision rectifiers and peak detectors. So, we're going to look at some precision rectifiers, super diodes, improved precision rectifiers, full wave precision rectifiers, and basically how to determine the average RMS and peak values using one of these full wave rectifiers. And then peak detectors, we will be looking at a normal peak detector and a buffered peak detector. So, the problem that we typically have with diodes is they have a zero point 0.7 volt drop. And if we want to measure extremely small signals, we don't want a zero point 0.7 volt drop, right? Because we can't measure anything below 0.7 volts then, especially if there is some AC signal that you need to measure. So if you need to measure really small signals, we can use the super diode. So basically you connect an op amp in a buffer configuration and place the diode in the feedback loop on the output. So for the top one, current can only flow out of the circuit, and here current can only be flowing inwards. Okay, so on the side here I have a sinusoidal input and the rectified version on top of it, and as you can see there is no 0.7 volt drop. The problem with this, however, is since you are limiting the current to one direction for the op amp, you can damage the op amp. Right, so we will be looking at how to fix this in a moment. Now, this solution right here, you can see that a transfer curve V out versus V in for any negative voltage, there is nothing that passes, and for any positive voltage, we have a one-to-one kind of slope. Okay, so what you get in is what you get out. Right. For the negative one, all the positive values is gone, and you get a one-to-one for the slope over here. Obviously, until the saturation limit. Now, the improved precision rectifier includes an additional diode. So we can have a positive voltage going out. Okay, and we can have feedback through this resistor here into our op amp here for biasing purposes. And we can have, for any negative signals, we can have current flowing back into the op amp. Okay, so the risk of damaging the op amp is reduced. There is then two nice things about this circuit is you don't risk the op amp, and with a negative feedback is you can add gain to your circuit. Right, so we have precision rectification with gain. The second thing that you can do is if you turn these diodes around, then you make it a negative diode. Okay, or in inverted commas, negative diode. This one is for positive signals. If you turn the diode around, it will be for negative signals, like the one right here. So a typical application is to take this inverting amplifier configuration with the rectification and put it through an integrator. With this integrator and the gain, you can tune this to give you the peak value, the RMS value, or the average voltage of a signal. This is good to condition a signal before it goes into a ADC for digital measurement, or if you only have a DC panel meter available, you can get the signal right to go into one of them. So this is a typical application of these precision rectifiers, is to condition signals for measurement, and especially if it's very, very small signals. Right, so in the simulation that I'll show you later, I set one up to measure a 2-volt signal, and here is our 0.63, here is our 1.41, and here is our 2-volt. So the peak, the RMS, and the average voltage as the output. Right, full wave precision rectifiers. Can ignore this capacitor here for a moment. That is to make this integrator. For full wave rectification, you need to combine a couple of concepts. So first, you will have a signal as it was originally, and you will add a rectified version to the original signal, making it a full wave rectifier. So this is a summing amplifier, inverting summing, and a precision diode. And adding the two signals, you will get a full wave rectification. Adding the capacitor here is the same as the previous circuit to make it the integrator, and so you can get out RMS or peak values from this. Another full wave rectifier is to take the input here, and only the positive half will enter here and exit towards V out. And since this is inverting amplifier, if you choose R1 and R2 to be the same, the negative will be outputted here as a positive, and you will get full wave rectification, which is not just a mathematical operation like this one, but actual full wave rectification. Okay, so this one will duplicate one of the waves to subtract from the other. This one will actually let through the signals rectified like they should be. Okay, so this is a much better full wave rectifier. Okay, then you can add a bridge in the feedback path. This is good for panel meters to do voltage measurements, and if you replace this panel meter with a resistor, you can do current measurements, and I will show you this in the simulation for the resistor, but it does do full wave rectification of any signal coming in. And the last topic is peak detectors. Sometimes you want to find the maximum in a signal and keep that maximum for a while. So you basically do a DC conversion and put it through a capacitor and a resistor with high values, and it will keep your value for a long time. With a larger capacitor, you can have less ripple on your signals. So in short, I inputted 3 different waveforms into this circuit, and small capacitor value and a larger capacitor value, and you can see the result here. More ripple with a smaller cap, less ripple with a larger cap. You can see that it charges as it follows a sine wave up until 5 volts, and then it discharges into the resistor. This next one is the refresh with a sinusoid coming in again. Okay, this becomes less and less with larger capacitors. Right, this is good for some applications, but if you want to find the peak and hold the peak for a long time, this is not ideal. So you can have a precision rectifier which stores the voltage in the capacitor, and the capacitor can't discharge that way. It sees infinite impedance in this direction, and this capacitor stays charged. Basically, the voltage is duplicated to V out for measurement and then fed back into this amplifier, keeping our capacitor at the level where we had it. So this circuit can keep the peak of a signal for a very long time. Right, so this is much longer than the previous application. And what you can do is you can use the circuit as a sample and hold. So if there's a bunch of peaks and you want to find where a peak is in a signal, you can basically get that value and this circuit will store it. Or if you want to do this at different time intervals, you can place a capacitor, a BJT over the cap with a monostable, whatever, and just periodically discharge the capacitor, and you can have your output refreshing every now and again. So let's go and have a look at some selected simulations of these circuits. So for our first simulation here, I have the two super diodes. I'm going to try and stick to the same format or order as the presentation of the simulations. So I'm first going to do a DC sweep over the two super diodes. One is positive, one is negative. Run this, and there they are. Okay, let's do a transient. And we are now looking at V out 2, so it gives out the negative wave. And this is a 1 volt sinusoid. And at this one, it gives out only the positive. Right, so these super diodes are quite cool. Let's look at the precision diode. So the next one here is our precision rectifier, and I turned the diodes around so that our output is negative and invert it again by this low pass filter. So if we run this, there's our input, 100 millivolts, and there is our outputs. I supplied 3 different resistors up here for different gains, so that I can do an average calculation, RMS calculation, and a peak value. So you can see that they are half-wave rectified, and only we get the negative part back. And when they are conditioned already, we put them through the low pass filter over here. We get our RMS up here, roughly our peak, and our average voltage out. If we turn the diodes around, we will get the inverted version. So all of these will become negatives. So there is our peak, our average, and you can see that this is only the positive half of a wave. So the full wave rectifier with a summing amp. Let me first remove this cap over here. If we run this, there's our input, plus minus 2 volts. And this will give the negative half. and this is in here only one time, and we need a reduced version of original signal going into this summing over here. So basically this double signal is added to this, creating our rectified version. But as you can see, this has some issues with imbalances in the signals, and you need to match the resistors quite precise for everything to be okay. So with a standard resistor value, this is not going to be working okay. So let's make that 20k. And if we run this and take the output 0.63, 1.4, and 2, with this integrator kind of setup, we can get our RMS, peak, and average values out of this circuit. So yeah, that is the one full wave rectifier, but this is not true full wave rectification. So let us go over to the other circuit that I had in the slideshow. That is the next precision rectifier. So if we run this, we'll find that we have our plus minus 2 volt in. Again with resistors for our integrator to provide our levels, but you'll see that these are all negatives. We'll fix that in a moment, but let's get back to the rest of the circuit. Okay, measure here, you'll see that we have full wave rectification. So there's half wave, there's the other half of a wave, and there is the result. Okay, so then the result passes through this low pass filter and provides us with peak, RMS, and average. And if we want to fix the fact that these was negative, we just turn these diodes around, run it, and now we have our negative cycle. Okay, so it's like taking a measurement on the other side of a diode bridge, and all of these will now be positive values. Okay, let's have a look at the bridge rectifier. Okay, this circuit works well with a panel meter, but in terms of extracting an actual voltage from this bridge is kind of difficult. But 100 millivolts through 1k would give you 100 microamperes. So it does do the full wave rectification, but getting anything more from this circuit is a nightmare. I will not recommend using this setup except for perhaps a panel meter if you don't want any losses. So yeah, that's it for the rectifiers. Let's go and look at the peak detectors. So here is my peak detector. It's super diode and then a resistor and a capacitor, and I went with a 10 microfarad and 100 microfarad and 3 different inputs, 1 volt, 3 volt, and 5 volts. You run this and have a look. We have our discharging happening quite rapidly with a smaller cap, and it's kept much longer for the larger cap. So if you would put a 1 milli in there, it will keep the signal for quite a long time. But also notice that it will charge in steps because the frequency is happening faster than the capacitor can charge up. So don't ever use too large values so that this can't keep up with a change in signal. So a change in signal, if I remember correctly, it's 10 times RC that you should choose your values with. So yes, but you can see that the output kind of discharges quickly into the next signal. So this is not necessarily something that you want. So, and this uses the diode configuration where we can damage the op amp. So let's look at the buffered configuration. So our buffered configuration, with our feedback applied, we protect the diode. It can do negative signals, no issue. And if we run this, look at that smooth line keeping the input. So you can see that it actually follows the input. So detecting the peak theoretically all the way and then just remains at that level. And this is just a 1 micro and a 10 kilo ohm resistor compared to the previous circuit. So even with a decrease in the resistor and capacitor, this is kept for a long time as well. No decrease of any sort. And this is on a 10 hertz signal, so the time between is actually quite large. Make this a 1 hertz signal, we would be able to see much better. Can you see that it follows and it holds it for a long time? They're not even at another peak and it's still keeping the output. Okay, so if you need to discharge this, just BJT over this capacitor, and every time you insert a pulse it will reset and then detect the new peak. However, this is for positive peak detection. If you want negative peak detection, you need to turn the diodes around. Okay, and that is it for precision rectifiers and peak detectors. Thank you for watching.